the last programme we looked at linkage mechanisms, devices which move in a constrained way. Structures are designed so that they won't move. When we think about structures or other objects that don't move, there are three questions to be addressed. What forces act on this object? How do we model the object? And what additional forces are needed to ensure that it won't move?
Let's look at the main forces that might appear on a free body diagram. First of all, the gravitational force, or weight force as we usually call it. This is calculated from W equals mg, where m is the mass in kilograms, giving W in newtons, and g is 9.81 newtons per kilogram on Earth. On the Moon, g is only 1.6 newtons per kilogram, so a given mass would weigh less there. Later in the course, we'll see where the value of g comes from. The weight force acts remotely, so there's no need for direct contact. Next come the solid contact forces, which you need wherever a solid object is in contact with the free body. If the solid object, such as a spring, is being distorted, then it exerts a resisting force. This is often modelled as a force proportional to deflection, F equals kx. Later in the course we'll look at that in more detail. Where two contacting bodies slide, or try to slide, there will be a friction force. This can be as big as μn, where n is the normal reaction perpendicular to the surface, and μ is the coefficient of limiting friction. Next come the fluid contact forces, when a gas or a liquid such as water is in contact with the chosen free body. Fluid static forces include forces such as those on locked gates, and vertical ones such as buoyancy, given by F equals rho Vg, where rho is the fluid density, V is the volume of the body, and G is gravity. If the fluid is moving, such as a wind around a building, or a car moving along through the air, or a ship moving through the sea, then there's a different pressure distribution and a different force. The extra force, compared with the static case, is called the fluid dynamic force. This can be very complex, and you can even get fluctuating forces in a steady fluid flow. This is the typical sort of equation used here. The force equals a force coefficient, like a drag coefficient or a lift coefficient, times a reference area, that might be the wing area on a plane or the frontal area of a car, times a half, times the fluid density, times the speed squared. Finally, we have the electrostatic and magnetic forces. These are particularly important in machinery such as electric motors and dynamos or alternators, but that's the subject of electrical engineering, and you won't come across these forces on this course. So, when you're drawing a free body diagram, you'll need to look out for the first 5 forces. Sometimes you can work out the actual forces by equations, such as these on the right. At other times, you need to use Newton's laws to relate the various forces on the free body. The equations on the right are just to give you a feel for the sort of equations typically used. Often finding these forces in engineering practice is very complicated. For example, the wind force on a building may be represented by this equation, but you need to know the force coefficient. You might be able to look up a reasonable value in a fluid dynamics handbook, but in many cases special wind tunnel tests would be required.
The second question we asked ourselves was, how do we model the object? Let's look at this wheelbarrow. The wheelbarrow designer needs to be sure that the barrow can be lifted, even when it's loaded. We model the wheelbarrow using a free body diagram. The free body diagram is a profile of the barrow, isolating it from its surroundings. In this case, I'm interested in the force that John exerts on the barrow as he holds it up, so I don't include him as part of the free body diagram. All this means that I need a free body diagram like this. I'm not interested in the interactions between the wheel and the main part of the barrow either, but I am interested in the reaction force at the floor which supports the wheelbarrow. No internal details are needed. We're only interested in the forces acting on the body, not the ones acting within it. So, for example, I don't show any wheel bearing forces. Next, I mark all the forces acting on the body. The weight force acts in a vertically downwards direction through the centre of gravity, which is the length A from the front contact point. It's equal to mass times G. There's a reaction force acting at the point of contact between the wheel and the floor, There's no possibility of slipping, so the reaction acts in a vertically upwards direction. I'll call that force N. Finally, there's the force that John exerts. I know that it acts vertically, so I'll represent its magnitude by F. It acts through a point which is B from the front contact point. Next, I select axes. I do this by looking at the forces acting on my free body and aligning my axes with as many forces as possible. In this case, it's a pretty clear choice. So, I've drawn a profile of the body with no internal details. I've marked the forces I do know, taking care with their lines of action and their points of application, and I've assigned symbols to represent the forces that I don't know. Since the body is static, I know that no net forces or moments act on it, so I can now apply conditions for the equilibrium of the body. There are no forces acting in the x direction. In the y direction, there's N, the weight force, mg, which is negative because it's acting downwards, and there's John's force, F, and they're equal to 0. Next, I can take moments. In this case, I'll take anti-clockwise moments about here. So we have mg times the horizontal distance a, and this clockwise moment, so that's negative, which is F times that horizontal distance b, and they're equal to 0. So there we are, 2 equations and 2 unknowns. It's quite easy to solve for N and F, and you can follow this up after the programme.
Now let's look at another simple example. This is a spring balance. The weight force from the load extends the spring. Because G is constant on Earth, these are usually calibrated to indicate the mass directly in kilograms. This particular balance actually indicates the weight force of the load in newtons. As you can see, the weight is 10 newtons. What will happen to the balance reading when I immerse the load in water?
To predict the spring balance reading, I need to use a free body diagram of the block. I begin by drawing a profile of the block. That's simple enough. Next, I need to consider the various possible forces on the block. Let's check John's list. There's certainly a significant weight force. This acts downwards, of course. Also, the block is in contact with the solid, the spring balance, which is stretched, so the spring exerts a force upwards on the block. I'll call that force T. I don't think there are any friction forces. Now, the fluid forces. There may be a fluid static force. The fluid is water, so this will almost certainly be significant. In this case, it would simply be an upwards buoyancy force, B. This buoyancy force is the result of a higher pressure here, pushing up, than there is here, pushing down. There are no fluid dynamic forces. Everything is stationary. To complete my free body diagram, I need to add the coordinate axes. Let's do the analysis. Applying Newton's second law, the total force in the y direction is 0 because of equilibrium. So the resultant force in the y direction is equal to T minus W plus B, and that's equal to 0 because of equilibrium. So if I can find W and B, I can find T. For such a simple shape, the volume is given by the sides, A, B and C. I know those. The mass is given by M equals the density times the volume. It's made of aluminium alloy with a density of 2,800 kilograms per metre cubed, so we can find the mass. The weight is W equals mg, where g is equal to 9.81 newtons per kilogram. So W, I happen to know, comes to 10. We've already seen that. The buoyancy force is given by B equals the density of the water times the volume of the block times G. The water density is 1,000 kilograms per metre cubed, and V and G I know. So I can get B, and it's equal to 3.57 newtons. So I can put all these into here, and I get that T is equal to 6.43 newtons. This is my prediction of the force exerted by the spring on the block. Is this what we want? Well, strictly not quite. We want the force exerted by the block on the spring. From Newton's third law, this is equal and opposite. Still of magnitude 6.43 newtons, but downwards.
Well, let's see what happens. The reading looks close to 6.43 newtons as predicted, so that agrees pretty well. One point to watch out for. You might be tempted to say that the weight has reduced to 6.43 newtons. This is definitely not correct. The weight force is still 10 newtons. It's the weight force minus the buoyancy that is 6.43 newtons. Now let's look at a real engineering example. One of the tests applied to new cars is to drive up and down a steep hill. Stopping and starting tests the ability of the foot brake and the handbrake. Let's try to work out the force that must be resisted by the handbrake when a car is parked on a steep hill. To do that, I'll draw the free body diagram of the whole car. Although the car is a complex collection of components, including a driver, it's perfectly valid to choose the whole car as a free body. Here's the profile at the appropriate angle, pointing downhill. The hill angle is theta. On an incline like this, it's nearly always best to align the coordinate axes with the surface. So I'll put my XY axes on like this. Now, what about forces? The first one is the weight force. Obviously, we aren't going to neglect the weight in this case. This point marked G is the centre of mass. We'll assume that the position of this is known, although actually measuring its position for a real car can be quite a complex operation. The weight force acts at the centre of gravity by definition. For most engineering purposes, you can take the centre of gravity to be at the centre of mass. It's only in very specialised cases that you need to consider the difference. For example, for some satellite motions. So I'll put the weight force here, acting straight down, of course. Now, from our list of possible forces, what about stiffness forces from solid contact? This gives us a normal force at each wheel, actually caused by distortion of the tyre and ground. The term normal has a precise meaning. It means perpendicular to the surfaces at the point of contact. So I'll draw on front and rear normal forces. Actually, of course, there are 4 wheels, 2 wheels on each axle. So NF is the force on the front pair of wheels. Now, what about friction forces? The handbrake acts on the rear wheels, so I need to add the friction force FR at the rear. I've shown FR this way. If it's really the other way, the maths will show me by giving it a negative value. What about the front? There could be some rolling resistance and bearing friction, which would cause a friction force at the bottom of that wheel too. But with the front brakes off, that force will be much less than the rear friction. For this simple analysis, I'll neglect it. That deals with the solid contact forces. What about fluid contact forces? The car is in contact with the air. There will be a small buoyancy force, actually about 50 newtons. And if it's windy, there'll be a fluid dynamic force too. But these should be relatively small, so I'll neglect them. So that completes the free body diagram. The car is stationary, so now we could do the equilibrium analysis to find FR. But I won't go through that detail now. Instead, let's look at a car when the air is moving past it. The moving air gives an aerodynamic force. We can test this in a wind tunnel, like this one at the Motor Industry Research Association, where we keep the car still and move the air, controlling the wind speed and measuring the forces. Let's look at the free body diagram for a car in a wind tunnel. This is the free body diagram with no air movement, with just the weight and the front and rear normal forces. With the air moving, there's an extra aerodynamic force that can be represented in various ways. Typically, the total force will be something like this. You can see this will change NF and NR. It also means that we need a driving force to resist the drag, for example here at the rear wheels. Now that representation isn't very convenient for analysis, so the usual thing to do is to take an aerodynamic origin here at ground level and to consider the force in components. So there is a horizontal component, the drag force D, a vertical component, the lift force L, and a pitching moment M, considered about this point. Knowing D, L, M and W, from this free body diagram we could use equilibrium to find NF, NR and T. I've shown L as upwards here, and most cars do have some lift, although racing cars are designed to have a big down force, because this increases the tyre vertical reactions, giving more grip.
So far we've looked mainly at the weight force and forces that act on the surface of a body, at the perimeter of the free body diagram. But engineers also need to know about the forces acting within a body. We still use free body diagrams, but this time they're chosen in a slightly different way. We went to talk to Roger Gibson at Bristol Polytechnic.
I'll be looking at the forces in the individual members of a pin-jointed structure. This framework is typical of the types of structure used to support loads. The engineer needs to know that the members of the structure are strong enough to sustain the loads imposed on a member safely. In particular, I should be looking at the forces in this member and in this member. To do this, I'm going to use a pin-jointed model of each of the joints of the structure. This is a typical pin joint, and you can see the pin here passing through the joint. Each of the members is free to move relative to each other without friction, so that the force in each of the members must act along each of the members. The first thing to do is to establish the vertical equilibrium of the structure so that we can find the weight of the structure. Vertical equilibrium states that the total upward force must be balanced by the total downward force. So by reading the spring balances at the end of the structure, I can find the weight. The spring balance at this end reads 120 newtons, and at the other end it reads 120 newtons also. So therefore the total weight of the structure must be 240 newtons. What happens if I were to load the structure with a 100 Newton weight at the center of the structure? The spring balance readings now read 170 newtons at this end and 170 newtons at that end, but I could have predicted that using a free body diagram.
To find the force in the two members, I draw a free body diagram of the pin in the corner. What forces are acting? Acting vertically upwards on this pin is the force exerted by the wire. I already know that it's 170 newtons from Roger's balances. I could have found that by applying equilibrium conditions to a free body diagram of the whole structure. Each of the members has a force acting within it, which may be a compression force or a tension force. I'll assume that they're all going to be tension forces, and I'll let the mathematics take care of it if they're actually going to be compression forces. For tension in the members, the pin forces are like this. F1 acting down there, and F2 acting horizontally there. I can apply equilibrium conditions to this free body diagram and find these forces. Working through a structure pin by pin like this is known as the method of joints. Here's Roger again.
I'm going to measure the forces in the members using strain gauges. A strain gauge is a small patch stuck onto the surface of a member, just like this one here. It consists of very fine wire closely bonded to the surface of the metal. And I've got here a piece of metal with a strain gauge stuck onto it. The idea is that if you apply a load to the member extends, and because the strain gauge is closely bonded, it extends as well, thus altering the electrical resistance. As you can see, if I were to apply a tension force to this, the reading comes quite high, and the effect is amplified by the fact that the strain gauge is in a zigzag like this, thus increasing the length and increasing the resistance effect. Of course, this is just acting like a spring, which you've come across previously in the course. And for a spring, the load is proportional to the extension. So by measuring the extension in this way, I can get a direct reading of the load. I've previously calibrated this member, which has a strain gauge on it, and this gives a reading of 1 digit on here for every 1 Newton of load. So that I can now read the forces in these two members directly on this meter. At the moment, we're reading the force in this member here, and you can see the reading is 246 newtons, which is a tension force. If I change to this member here, you can see that the reading is minus 162, which corresponds to a compression force in this member of 162 newtons.
Could I have got that answer using a free body diagram analysis? Well, vertical equilibrium relates this force to the resolved part of that force, F1 sine 45, and the sum of those is equal to 0. Horizontal equilibrium relates F2 to the horizontal part of F1, which is F1 cos 45, and that too is equal to 0. I can quite easily solve these equations. I can get F1 from that equation. If I put it in there, I can find F2, and I get the answer that F1 is equal to 240 newtons and F2 is equal to minus 170 newtons. The minus sign indicates a compression force. These values are slightly different from Roger's, probably because this isn't a perfect pin joint, and there might be inaccuracies in the strain gauges as well. Let's go back to our 3 questions. What forces might be acting? We've looked at those. How do we model the static structure? We use a free body diagram. What forces are needed to keep it still? We use horizontal, vertical and rotational equilibrium to find the unknown forces.